With interest in PFAS continuing to escalate at an extraordinary pace, so too has the interest among environmental stakeholders to augment and grow the PFAS analytical toolkit. Today, I'll be presenting on the current offering of tests or tools available for determining PFAS in a variety of environmental matrices and for a variety of needs. Before I begin, let me introduce myself and Bureau Veritas. My name is Terry Obal, and I'm the Chief Science Advisor at Bureau Veritas in Canada. My role is to ensure that sound science and its value are fully available to our customers, regulators, and the public. Bureau Veritas is the global leader in testing, inspection, and certification. Our mission is to shape a world of trust by reducing clients' risks, improving their performance, and helping them innovate to meet the challenges of quality, health and safety, environmental protection, and social responsibility. I'll begin this presentation with a short history of the growth in environmental interest in PFAS. By doing so, the scope and complexity of the problem this class of compounds presents for analysts and environmental stakeholders will become apparent. Where it began. It began many years ago with the discovery of two particular compounds in human blood, perfluorooctanoic acid and perfluorooctane sulfonate, or perfluorooctane sulfonic acid. The acronyms PFOA and PFAS are very common in the world of PFAS, and I've equated the two compounds with Teflon and Scotchgard. That's how these compounds were initially presented, and that allows the public to relate to them. However, be very careful. Perfluorooctanoic acid is not Teflon, and perfluorooctane sulfonic acid is not Scotchgard, but rather they are building blocks. They are used in the manufacture of the materials Teflon and Scotchgard. But as I said, so that the public can relate to the compounds, oftentimes they were presented in the media as Teflon and Scotchgard. But it began with really interest in these two compounds, PFOA and PFAS. But the interest grew as people started to recognize that there were other per and polyfluorinated alkyl substances. Two examples are perfluorobutanoic acid and perfluorononanoic acid. But there are many other straight chain and branched per and polyfluorinated alkyl substances. But the interest grew, and people started to become interested in precursor compounds like 8,2-fluorotellumer alcohol or 6,2-fluorotellumer sulfonic acid, and a plethora of other compounds that have been demonstrated to, over time, transform to the stable and in fact, very recalcitrant end products presented in the first column. So as you can see, the interest and the complexity in the problem is growing. As toxicologists started to demonstrate that the recalcitrant, the stable end products presented in the first column were showing toxic effects or were related to toxic effects in animals, the manufacturers decided to unilaterally decided to sunset these chemicals and reduce their use to the point of eliminating their use. But the benefits of these compounds were shown, so they began manufacturing replacement compounds. And the replacement compounds, people have started to question the toxicity of the replacement compounds. Manufacturers would have us believe that the replacements, being shorter chain, lower molecular weight compounds, are less toxic than the stable end products presented in the first column. However, the scientific evidence is beginning to demonstrate that they do exert a toxic effect, and at times, and in some cases, are just as toxic, if more so, if not more so, than the compounds that they were replacing. But you also have to consider risk. These compounds, the replacement compounds, being lower molecular weight, exhibit higher solubility than the longer chain, higher molecular weight compounds that they were replacing. So with respect to hazard versus risk, the replacement compounds, while they may not be as toxic, but they are toxic, but they are certainly far more mobile. So these can present a greater risk than the compounds in the first column. All in all, the class of compounds, PFAS, it's been suggested that this is composed of 5,000 or more compounds. And as a result, it becomes very complex trying to navigate this class of compounds and the hazards and the risks that they present. So in order to address this plethora of potential contaminants in the environment, scientists have developed techniques to measure, either directly or indirectly, total PFAS. This evolution of measurement techniques, what I've referred to as the PFAS toolkit, follows the growth in compounds of concern that I presented in the previous slide. It began with the analysis of individual PFAS, so looking at specific compounds. And the technology used there is liquid chromatography coupled with tandem mass spectrometry, LC-MS-MS. So the analysis of individual PFAS compounds like perfluorooctanoic acid or perfluorooctane sulfonic acid, PFOA and PFOS, would be analyzed, and it's been recognized as a best practice that these compounds are analyzed at ultratrace levels using liquid chromatography with tandem mass spectrometry. But as the interest in a broader spectrum of PFAS grew, the requirement for other approaches to analyzing them also developed. So the analysis of individual PFAS by liquid chromatography, tandem mass spectrometry, evolved into what is referred to as the TOF assay, the analysis of total oxidizable precursors. In essence, this approach is analyzing the sample using liquid chromatography with tandem mass spectrometry, then submitting a duplicate sample for oxidation, where you oxidize precursor compounds to the end products. And this provides a picture of an indication of other PFAS in your sample that may not have been analyzed for using the PFAS by LC-MS-MS. PFAS by LC-MS-MS is a targeted analysis where you're looking at specific compounds. Total oxidizable precursors, not only are you looking for the target compounds, but it provides an indication of other PFAS not measured, not targeted, that may over time transform to the compounds of interest. And this now has evolved to total organic fluorine. There are different approaches to analyzing total organic fluorine, and in this case, the intent is to use organic fluorine as a proxy for PFAS in your sample. So it provides a more holistic measurement of PFAS in your sample over and beyond the target compounds analyzed by LC-MS-MS. As I said, there are different approaches to analyzing for total organic fluorine. The first is neutron activation analysis, and in this case here, you are activating the sample, you're bombarding it with neutrons, and then measuring the gamma radiation being emitted by the activated sample. The challenge with this approach is, as you can see from the photograph above the instrumentation, this nice blue glow, well, that's a nuclear reactor. So you need a nuclear reactor to be able to perform this analysis, which we have access to through a local university. but not everybody has access to a nuclear reactor, so this is not necessarily the most practical approach to analyzing total organic fluorine. Another approach developed and certainly advocated by Graham Peasley at Notre Dame University is particle-induced gamma-ray emission spectrophotometry, or as it's affectionately known, PIGGY. It provides an indication, or it measures total fluorine in a sample. So if you can partition the organic fluorine from the inorganic fluorine, this provides a viable and sensitive approach to analyzing total organic fluorine. The challenge is the capital costs associated with this analysis. Probably one of the more pragmatic approaches to analyzing total organic fluorine is combustion ion chromatography. And so I'll be speaking to that approach. So in the next several slides, I'll present some details about these three analytical approaches to measuring PFAS, as well as how they are typically applied in the environmental marketplace. The recognized industry best practice for measuring individual PFAS at ultratrace levels remains liquid chromatography coupled with tandem mass spectrometry, or LC-MS-MS. And the industry best practices, the approved methodologies, are typically based on isotope dilution, solid phase extraction, liquid chromatography with tandem mass spectrometry. Isotope dilution is where the samples are spiked with isotopically labeled analogs of the compounds of interest. The samples are extracted through a solid phase extraction system or through a medium that cleans up your sample and concentrates the analytes of interest, and then analysis by liquid chromatography with tandem mass spectrometry. The benefit of this approach is the ability to analyze at very, very low levels. The reporting limits for PFAS by LC-MS-MS using isotope dilution solid phase extraction techniques are typically at the low part per billion levels for soils and at the low part per trillion levels in water. Those are the reporting limits. The method detection limits are subpart per billion for soils and subpart per billion or subpart per trillion for waters. Now, it has to be recognized that at these reporting limits, at these trace levels, it is important to consider the ubiquity of PFAS. The PFAS has been so the use of PFAS has been so prolific in consumer products and in industry that it's everywhere. So it's very important to eliminate any sources of PFAS. So I will comment that this makes having a robust laboratory and field quality assurance program a must. So how are these concentrations of individual PFAS used? So analyzing PFAS by liquid chromatography with tandem mass spectrometry is primarily applied in characterizing PFAS contamination and demonstrating compliance with guidance values, or more increasingly what we're seeing is regulatory standards. So there is rapidly a migration from guidance values for PFAS and environmental matrices to various jurisdictions now regulating the concentrations that are allowable in matrices like drinking water or groundwater. So the ability to accurately and reliably measure to the low part per trillion level afforded by LC-MS-MS techniques is a requirement in more and more jurisdictions. As you can see from some of the regulatory standards, they are being driven lower and lower into the as new toxicological information comes to light. The regulatory standards are being driven lower and lower, and as you can see, they are at the low part per trillion levels. The total oxidizable precursor assay For this assay or for TOPS, you're still using the approach of measuring individual PFAS by LC-MS, but now you're doing it twice with an oxidation step in between. So this is a protocol that was developed by Erica Hodson and Dave Sedlak out of the University of California in Berkeley and published in 2012. And it is an approach that mirrors the behavior of higher molecular weight PFAS not measured by PFAS using LC-MS, and mirroring how these compounds perform in situ. It's known that these compounds can transform over time to the end products, the target compounds that are measured by LC-MS. So the total oxidizable precursors assay, the sample is oxidized, that accelerates this transformation process, and then the difference in PFAS concentrations is measured in the second sample. So this change in PFAS concentration is representative of higher molecular weight PFAS precursors that may over time convert to the lower molecular weight dead end PFAS. So how is this applied? Well, first of all, the first analysis, the analysis of one of the duplicates with no oxidation, provides a baseline for the results, baseline concentrations of the compounds of interest. And it should be recognized that it's like doing PFAS by LC-MS as shown in the initial approach. So these could be used for regulatory compliance purposes. What's important to note is two precursor compounds, two known precursor compounds, 6,2-fluorotellumer sulfonic acid and 8,2-fluorotellumer sulfonic acid, are measured at 210 and 380 parts per billion in this particular sample. This particular sample being an example. It's an actual sample that has been reported, and certainly the customer information has been redacted. But you can see in the original sample, you have concentrations of precursor compounds. The duplicate sample is then submitted for oxidation and oxidized over a period of time at elevated temperatures and then analyzed. And as you can see from the analysis of the oxidized sample, the concentrations of 6,2-fluorotellumer sulfonic acid and 8,2-fluorotellumer sulfonic acid have been reduced to non-detectable concentrations. But as you can see, the lower molecular weight carboxylic acids have shown significant increases from the baseline concentrations analyzed in the unoxidized sample. So what this suggests, and this is the basis for the total oxidizable precursors assay, is that the 6,2 and 8,2-fluorotellumer sulfonic acids have been transformed to lower molecular weight end products. But if you look at the concentrations of these lower molecular weight end products, they're substantially higher than what you would have expected from just those two precursors. So what this indicates is there are additional higher molecular weight compounds that are not measured by PFAS using LC-MS techniques. And so this is where the value of the TOPS assay comes to the forefront, in that it provides an indication of other PFAS not measured as part of your target compound list that may over time transform and manifest itself in future liability for the stakeholders. At this point, I'm going to stop for a moment to speak about this concept of PFAS dark matter. It's a euphemism for the higher molecular weight compounds that are not measured. Typical PFAS analyses by LC-MS-MS report 20 to 50 PFAS compounds. Some academic institutions are now reporting much higher numbers of different compounds. They've characterized up to 200 different PFAS. But from a commercial laboratory standpoint, typical PFAS analyses report 20 to 50 PFAS. And it's well understood, as we've shown in several slides previously, that there are thousands of PFAS compounds present in the environment, and most of them are unknown or uncharacterized. Hence the concept of dark matter, the material that is out there, but we're not measuring. So PFAS dark matter can, as I've said, break down or transform into PFAS that are measured and that we do have toxicity information on. But what's also very important to recognize is that this dark matter can contribute to toxicity risk beyond that identified by the PFAS by LC-MS target compounds. So by accelerating this transformation process and identifying dark matter, it helps the decision makers or the environmental stakeholders to evaluate their toxicity risk more accurately. So how do you accurately assess the site risk or required remedial effort with this unknown? As I said, the total oxidizable precursors assay gave us a glimpse of the dark matter, but most now agree it's not a complete solution. It's not a panacea. It's not fully quantitative, and there is the potential for high sample variability, particularly if there has been any sort of in situ remedial action using chemicals, be it ISCO, in situ chemical oxidation. And TOFs does not necessarily capture all of the dark matter or all of the higher molecular weight compounds. So what's the answer? The answer, total organic fluorine. And this is the third approach that was presented in the evolution of the PFAS analytical toolkit. The first commercially viable combustion ion chromatography total organic fluorine method was published by von Abercrombie in 2019, where he looked at total organic fluorine using combustion ion chromatography and compared it to the potential fluorine contribution from the PFAS measured by LC-MS-MS. Essentially, combustion ion chromatography, it's a semi-automated solid phase extraction. This partitions the organofluorine from inorganic fluorine. The partitioned organic fluorine is then combusted at temperatures above 1,000 degrees Celsius, which most will recognize that that's probably the most effective way for treating PFAS in the environment is high temperature incineration. Well, that's effectively what's going on in the combustion unit, is you are incinerating the PFAS at high temperatures and thereby mineralizing the molecules and forming fluorine, which is converted to hydrofluoric acid. It's trapped in water. The water is then analyzed by ion chromatography for fluoride. Using this approach, what von Abercrombie showed is that the total organofluorine burden in wastewater is typically 100 times higher than what would be suggested by summing the PFAS measured by LC-MS-MS and then calculating the theoretical fluorine concentration. So as you can see from the histogram, the dark bars represent the fluorine concentration expected from the PFAS measurements by LC-MS-MS. What the lighter bars in the histogram show is the actual organic fluorine measured by combustion ion chromatography. So what that shows is there's a lot of PFAS in these wastewater samples that is not being measured by LC-MS. What do the total organic fluorine results mean when measured by combustion ion chromatography? Remember that total organic fluorine by combustion ion chromatography, you're measuring the fluorine contribution from all of the fluorine-containing compounds in the sample. So if you consider PFAS, perfluorooctane sulfonic acid, you have 8 carbons, 17 fluorines, a sulfur, and 3 oxygens. And this is the conjugate. The acid form would have a hydrogen in there. PFAS by LC-MS, you are measuring PFAS. When measuring by combustion ion chromatography, you're measuring the fluorine contribution. So it's important to recognize that the fluorine contribution is really 65% of what's measured by PFAS. So it's not a direct correlation, PFAS by LC-MS and fluorine by combustion ion chromatography. So if you were to measure 250 nanograms per liter of PFAS in your sample, the theoretical organofluorine contribution would be 162 nanograms of per liter of fluorine. So that's important to recognize. It's not a direct one-to-one relationship. We've done studies, and this is just a typical sampling of 3 real-world samples. These are groundwater samples, and in the first, 6,2-fluorotellumer sulfonic acid was measured, perfluorooctane sulfonic acid, and the C6 form of the sulfonic acid, perfluorohexane sulfonic acid, were measured at the concentrations shown in this slide. Calculating the organic fluorine, the theoretical organic fluorine from the sum of the PFAS, one would expect 15.7 micrograms per liter of fluorine. When measuring when the sample was measured using combustion ion chromatography, the result was 23. So that's showing an increased concentration about 1.5 times, indicating that PFAS by LC-MS is not measuring all of the organic fluorine. And if the assumption, and it's a pretty solid assumption that the organic fluorine is coming from PFAS, there are other organofluorine compounds certainly in agrochemicals and in the pharmaceutical world. But this is providing an indication that there's more PFAS in your sample than is being measured by LC-MS. A more compelling example was this sample MW12. It's a monitoring well where PFAS was measured at 3.5 parts per billion, perfluorohexane sulfonic acid at 1.1. The theoretical organic fluorine from the LC-MS results was 2.9 micrograms per liter. Measuring total organic fluorine by combustion ion chromatography, the result was 50 micrograms per liter. So it represents a 17 times increase, indicating that there are more PFAS in your sample that are being measured. And the final example is an AFFF. One of the most common sources of PFAS in the environment are aqueous film-forming foams or firefighting foams. And in this case, this sample is called Petrosil 3%. Being one of the primary components of AFFFs, it's the 6,2-fluorotellumer sulfonic acid, was measured by LC-MS at 53,000 micrograms per liter, so 53,000 parts per billion or 53 parts per million. The other compounds, if there, were diluted out of the system. So the theoretical organic fluorine from the 6,2-fluorotellumer sulfonic acid was 30,500 micrograms per liter. What was actually measured by combustion ion chromatography was well over 2.4 million parts per billion of total organic fluorine. And so this represents greater than 80 times what was measured by LCMSMS. And the 2,400,000 micrograms per liter makes sense if you consider that the 3% in the name probably represents the percent of alkyl fluorinated surfactants in that sample. So if we go back to the evolution, the complexity of the PFAS problem in the environment, PFAS by LCMSMS will measure individual target compounds in your sample. As long as you have a standard that you can calibrate the system. So it's typically used for the end products, the recalcitrant or very stable PFAS. It's used to characterize some of the precursors, and it is more and more often being used to measure the replacement compounds like Gen X or F53B or Adana, as shown here. The total oxidizable precursors assay, not only will it measure individual PFAS, it gives a glimpse of the 5,000 plus other compounds that are not measured as part of the target compound list. And then finally, total organic fluorine by combustion ion chromatography gives a more comprehensive picture of PFAS in your sample. It is not selective, but it gives you a measure of this organofluorine burden in your sample, which can be used as a proxy for PFAS. What are some of the advantages and limitations of these three approaches? If we consider PFAS by LCMSMS, where it's used to, the problems that it's used to address is typically characterization and quantitation of individual PFAS at ultra-trace levels. It's used for regulatory compliance and for risk assessment. And it offers advantages in that the measurements are accurate concentrations for individual PFAS. The reporting limits are down at the low part per trillion, and method detection limits below the part per trillion into the high part per quadrillion level. But there are limitations. It's a higher cost test. The LCMSMS is a high capital cost approach. It's a targeted analysis, so it only looks at the compounds that you have targeted and have standards for. And this is typically represented by 30 or 40 or 50 individual compounds out of a potential 5,000 plus PFAS. The total oxidizable precursors assay, it's used as well to characterize and quantify individual PFAS at ultra-trace levels, and therefore could be used for regulatory compliance. But by taking a duplicate of the sample that's analyzed and oxidizing it, then measuring PFAS again and evaluating the differences, the increases and decreases in specific target compound concentrations, it gives an indication of total PFAS. So it lets you know if there's something else that you might want to be worried about. What are its advantages? As with the single PFAS by LCMSMS analysis, it provides accurate concentrations of individual PFAS. It indicates the presence of PFAS not measured by LCMSMS, i.e. the dark matter. What are the limitations? Same high cost. You're using LCMSMS, but it's actually higher than PFAS by LCMSMS because it's a very labor-intensive assay. That leads to longer analytical turnaround times. There's high sample variability, not necessarily fully quantitative, and it doesn't necessarily provide a total PFAS result. That's why it's careful to say that it indicates total PFAS concentration. Total organic fluorine by combustion ion chromatography, it gives a measure of total PFAS. Is my sample, it answers the question, is my sample PFAS free? So the advantages of total organic fluorine by combustion ion chromatography is that it provides concentrations of organic fluorine, which is representative of the presence or absence of PFAS. It's less labor intensive than the TOPS assay, and it's certainly a lower priced analysis. The limitations, the current reporting limits for water are 600 nanograms per liter, so it's subpart per billion, but it's about 10 times higher than the currently accepted guidance values, and in some cases regulated values for PFAS and PFOA at 70 parts per trillion. Soils, the current reporting limits, it's at 200 to 700 parts per billion in soil. And the other limitation, it is not a selective analysis. You won't get individual compounds, but you will get a measure of that total PFAS in your sample. So when do you use which tool? And this has been covered in previous slides in different forms, but to bring it all together, if you're concerned about regulatory compliance, the individual PFAS are regulated. So you want a test that provides you with concentrations of individual compounds that you can then compare to the regulatory standards. If you are concerned about site characterization, what is contaminating my site? Then again, you may want to look at individual PFAS to characterize the type of contamination, and that could also be gotten from the TOPS assay. But because you're paying a premium on the TOPS assay, you're also getting an indication of other compounds, although not specific, on your site. If you are trying to delineate the extent of contamination on a site, if you're looking to delineate the extent of contamination of individual PFAS, then certainly analyze your samples using liquid chromatography with tandem mass spectrometry. If you are trying to delineate the extent of contamination of individual compounds and potential other higher molecular weight PFAS, then you would use the TOPS assay. Total organic fluorine by CIC, again, not a selective analysis. It is more a gross analysis for total or organic fluorine. But if that's all you're concerned about is how far does the contamination go with, and just using fluorine as a proxy for PFAS, this is a very practical and low-cost approach to delineating contaminant or contamination on your site. Now, if you're considering how complete is my remedial action, you might want to, you might use PFAS by LC-MS if all you're concerned about is a specific compound or a specific group of compounds that are measurable by LC-MS. But you would probably be looking more so at the total oxidizable precursors assay, where you will get a measure of target PFAS, and you will have an indication of how effective your remedial action is, or your remediation is, on the overall, the total PFAS on your site. And if individual PFAS is not a big concern, total organic fluorine by combustion ion chromatography provides, again, a very practical and economically achievable approach to measuring, is my sample PFAS free? When it comes to site risk and future liability, TOPS assay or total oxidizable or total organic fluorine by combustion ion chromatography. Because in the first analysis, PFAS by LC-MS, you are not measuring compounds or material that could potentially transform to the compounds of interest. And then finally, if you're looking at samples to determine if they're PFAS free, considering things like AFFF, or more and more interest now is, or interest is growing now in consumer products. Is it PFAS free? You would want to look at total organic fluorine by combustion ion chromatography. So the Bureau Veritas PFAS toolkit, where does it stand right now? PFAS by LCMSMS is we have been reporting PFAS in environmental matrices and in some consumer products for many years now. This analysis reports, as I said, specific PFAS chemicals with low reporting limits. It's a higher priced analysis, kind of mid-range between TOFs and combustion ion chromatography. Our methods are compliant with modified EPA methods 537.1 and 533.1. And Bureau Veritas is accredited in Canada by the Standards Council of Canada, in many U.S. states through NELAP, and we are accredited by the U.S. Department of Defense to their Quality Systems Manual version 5.3. Total oxidizable precursors assay is offered through our Bureau Veritas laboratories. Again, reporting specific PFAS chemicals with low reporting limits before and after sample oxidation to simulate natural process. This is a higher priced test because of the labor intensity, but the analysis by LCMSMS, as with the first, are compliant with EPA methods 537.1 and 533.1. The TOPS assay is accredited in Canada by the Standards Council of Canada and in the US by the National Environmental Laboratory Accreditation Program, NELAP. DoD doesn't offer accreditation for TOPS yet. And then finally, total organic fluorine by combustion ion chromatography, where you report the total organic fluorine from all PFAS in the sample. This is a low-cost analysis relative to the other two. There is no current EPA method. We are working with the EPA and sharing information to come up with a harmonized and standardized approach. Bureau Veritas' method is based on the ISO 9562 method from 2014, which is determination of absorbable organically bound halogens. And we are accredited through Standards Council of Canada for total organic fluorine by combustion ion chromatography, and accreditation in many of the United States is pending. Now, as Chief Science Advisor, if you'll indulge me one more slide, I have the opportunity to engage many people, and it's a privilege to work with some really, really smart people. So I always take the time to acknowledge the folks who do the work. And in terms of the analytical methods and operations for PFAS by LCMSMS and the total oxidizable precursors assay, Adam Robinson leads that team with Sin-Chi Chia, Colm McNamara, Alicia Wilson. Our project management team, Stephanie Paulin is our accounts manager. Lori Dufour is our project manager. Research and development, so a lot of the work for total organic fluorine by combustion ion chromatography has been performed under Heather Lord, who manages our environmental research and development group, and Lucy Kachatrian. If you have any questions or require additional information, please feel free to contact Stephanie or myself at the contact information provided. That concludes my presentation. On behalf of Bureau Veritas, I thank you for your attention.